So the first one that I'm going to look at is this one. Interconverting calories and glucose. So we have a few different conversions that we have to do. Alright, so this says a cup of green cooked peas is 1.25 times 10 to the 5 calories. 1.25 times 10 to the 5 calories. So the easiest ones to do are just going from calories to kilocalories. We just have to either multiply by 1,000 or divide by 1,000. Okay. So if we're going from calories to kilocalories, we're trying to find kilocalories. So 1 kilocalorie is the same as 1,000 calories. So notice our pattern. If we're going from calories to kilocalories, we're going to divide by 1,000, or we're going to subtract 3 off of this number. Okay. So this will be 1.25 times 10 to the 2. Yeah, there you go. I subtracted 2 instead of 2. And that's going to be kilocalories. Okay, are we okay there? So we're just converting between calories and kilocalories. That's just a difference of 1,000. So same number, 1.25, and then times 10 to the 2. And it has the unit up here on my table, so I don't have to put it after the number. Okay, and then this one, we're going to use this conversion. So we have this number, 1.25 times 10 to the 2 kilocalories. So we need to use this ratio, this conversion. So I'm trying to get to kilojoules, so that needs to go on the top. So kilojoules needs to go on the top, because that's what I'm trying to find. And I want to cancel out kilocalories, so that needs to go on the bottom. So 1 kilocalorie for 4.184 kilojoules. Okay, so this is just a unit conversion. So I'm going to do this on my calculator. So I'm going to take my number. Is it going to work? Okay, copy my number into my Alex calculator. And then I'm going to divide by, or multiply by 4.184. Okay, and then so it tells me the number. This is another one that on the test it's not going to tell me the significant digits. So we have to practice. This has 3 significant digits, so all the rest of them need 3. So we'll just put our number. 523, and then make sure you put the decimal. Alex likes that decimal. What's up?
Question 1 and question 2 are the exact same.
Yeah.
Oh, nice. So what's this one then? Okay, good. So we're noticing that this, if we times it by 100 times 10 times 10, we'll get this. Good. So we don't even have to do this. That was very nice of them to randomly give us the same one twice. Okay, if we didn't have this, let's do this if we didn't. If we didn't know that, oh, we already did this problem. 125, this is kilocalories. Then we're going to say, oh, we need it in calories, so there's 1,000 calories for 1 kilocalorie. So kilocalories cancels. This will end up being 1.25 times 10 to the 5th. With the decimal 1, 2, 3, 4, 5. We catch that? Good observation. So this is going to be the same number. We just did this one. Oh, 5. Okay, this one is a baked potato. It is 920 kilojoules. So now we need to go the other way. Let me go over here. So we're going to start with 920. This is kilojoules, right? Kilojoules. Okay, so the first thing, I think it's easier to go one box and then the next box. So we're gonna go to kilocalories. So what we're trying to get to kilocalories. What does the unit conversion need to look like here? Okay. Good. Kilojoules. So kilojoules cancels out. We'll end up with kilocalories. So this will be 920 times 1 divided by 4.184. 920. Oh, I put that in the wrong box. I'm trying to put it in my calculator. Read my mind, Alex. 920 divided by 4.184. Okay, and then this has 3 significant digits, so this number has to have 3. We can just keep 220. I think that will work. We'll check and see if that works. So we just need to keep 3. And then this one, we need to multiply by 1,000. So 220 kilocalories. kilocalories. So for 1 kilocalorie, that's the same as 1,000 calories. I'm trying to get to calories, so I'm going to multiply by 1,000. So let's do this on the calculator. Let me show you. This is pretty nice. Oh. So 220 times 1,000. And then I can just make Alex do this, put it inside the big machine. So I am liking this. I don't have to think about it. It just does it for me. And then we need 3 decimal places, or 3 significant digits, not decimal places. 3 significant digits. So this is going to be 2.2, add a 0. Yep, good, thanks. And then times 10 to the 5. Okay, let's check it. Okay, questions on that? Okay, do you want to do another one? Or are you ready to do the next one? Do another one. Okay, let's do another one. I'm going to close the door. Oh. Alright, so same type of thing. Alright, a kiwi fruit has this many calories. Keep moving my erasers. So I already used these numbers up here. Let's make sure that we know where to find this number if we need it. If we forgot it, we didn't write it on our note card, you can go to the data. And then this is conversion factors for, I think it's something non-standard. Is it in here? No.
I think it was at the bottom.
Oh, was it? Did I miss it? Yeah, right there. Oh, here it is. Okay, thank you. So for a calorie, it's 4.184 joules. So if you forgot that, you could look it up in Alex. I would still, if we're going to use this, you know you're going to use this on the test, I would just write it on my note card. So I don't have to look for it, but it is there. Okay, so we're going to write this number down. We have this number, 4.50 times 10 to the 4. That's calories. We need this in kilocalories. Oops. So we're going to put the unit conversion of kilocalories on the top. So 1 kilocalorie for 4.184 kilojoules. So this is this number. Oh, go. What are we doing? This is calories. I'm just doing the wrong unit conversion. There you go. 1,000 calories. So this is, we're going to take this number, divide by 1,000 calories. So calories is what we're going to do. So what we're going to do is we're going to divide this by 1,000. This number is going to go down by 3. So it would be 4.5 times 10 to the 1, which ends up just being 45. And we need 3 significant digits. Okay. All right, then we're going to take this number and we're going to convert it to joules. Now we're going to do the unit conversion I was trying to do earlier. So 4.184 kilojoules for 1 kilocalorie. I'm putting this on the top because that's what I'm trying to find. I'm putting this on the bottom because I need to cancel that out. And then I can get my answer. So calculator 45 times 4.184. Okay, and then 3 significant digits, so I'm just going to keep 188. Okay, question so far. All right, next one. So on the test, it's also going to be like this. You're going to have one of each number and you have to fill it out. So I like to go this way first. So we have kilocalories, 30 kilocalories. We need to figure out how many calories that is. Well, there's 1,000 calories for 1 kilocalorie. Kilocalories cancels out, so I have it in the right spot. And then 30 times 1,000. So I'm going to just write this out. 30, and then move my decimal 1, 2, 3. And then move it back. 1, 2, 3, 4. So 3.0 times 10 to the 4. Did I do that right? Also, we need 3 significant digits. So this one will have an extra 0. That's calories. .00 times 10 to the 4. Okay, and then we need to go the other way. We need to take 30 kilocalories and we need to convert to kilojoules. So kilojoules also on the top, 4.184. Oops. Kilojoules on the top for 1 kilocalorie. So we can cancel out the kilocalories. So 30. Oh. 30 times 4.184. And then we just have to round this to 3 significant digits. So 126 decimal. Okay, and then we have one more row to do. So this one we start with 607. I'm just going to put it right here. This is where we have some space. 607 kilojoules. I need this first in kilocalories. So I'm going to put kilocalories on the top. 1 kilocalorie for 4.184 kilojoules. Kilojoules on the top and bottom. That's how I know I have the unit conversion in the right spot. And then 607, excuse me. 607 divided by 4.184. Okay, we need that. Was that right? That's right. Okay, that seems right. 3 significant digits. 145 with the decimal. 3 significant digits. Okay, then I need to take that 145. 145 kilojoules. I need to convert that to, this is not kilojoules, this is kilocalories. We need to convert that to calories. So we need that on the top. 1,000 calories for 1 kilocalorie. So kilocalories cancels out, we'll end up with calories. I'm setting that up right. I'm going to type this into my, not that box, this box. 145 times 1,000. And then I'm going to use my scientific button to convert to the correct scientific notation, and I need 3 significant digits because the number they gave me has 3. Okay. All right, let's check this. Make sure I did it right. Okay. Something that I've noticed with these questions is often they have similar numbers. So like these are all 3 digits. These are 2. This one is 3, but they're all 3 significant digits. But then you can use those kind of as a pattern. Okay. So if the number they give me a 30 and I end it not 30. If they give me a number that has 2 digits, like a 10s and a 1s, then it's going to match times 10 to the 4. So they should all be pretty similar. Does that make sense? So that's one way to check. If you get like a 7 out of this one, then like that doesn't seem like it's matching the other numbers. Does that make sense? So use the other numbers in the other rows to kind of make sure that you're doing it correctly. Okay. Also, none of these should be negative exponents. So if you are getting negative exponents, probably you're dividing when you should be multiplying. Okay. Questions on this one? Are we okay to try another one? Okay. All right, I'm gonna move to the next topic. Let me remember which one we're gonna do. Calculate the heat of reaction from the molar reaction enthalpy. Okay, so we need to take a few notes to understand what's going on here. So I'm gonna switch to my slides. Okay, I would just write down the most important things. You don't have to write everything. So this is just kind of to give us an idea of what's going on. I'm just going to jump to the right place. Okay. So this part we're talking about breaking and forming bonds. So every time you break a bond, it takes energy. So that's called a cleaving a bond. That takes 58 kilocalories per mole for this chlorine bond, chlorine gas molecule. Okay. So we're adding energy that takes energy to break a bond. Okay. If we are running the reaction in reverse, when we put these 2 chlorine atoms together, we are releasing energy. Okay, when you put atoms together to form a bond, that releases energy. Okay, notice it's the same amount of energy, so we're either putting that energy in or we're getting that energy out, depending on if we're breaking the bond or forming the bond. Sometimes this seems confusing when you're like doing the assignment or you're on the test. So to remember this, when I'm breaking a bond, I think about like breaking a pencil. If I break a pencil, I have to put energy in. Okay, same with a bond. If I'm breaking a bond, you have to put energy in. When you make a bond, you're storing energy in that bond. Energy is released. Okay, so hopefully that kind of makes sense. So we're going to start talking about this delta H. This is the enthalpy of the reaction, okay, or the heat of the reaction. And this tells us how much energy is added to the reaction or released from the reaction, okay? So when it's absorbed, when we're putting energy in, so something like breaking a bond, that's called an endothermic reaction. So that's something that if you do the reaction, it gets cold. So have you ever felt one of those ice packs that gets cold? That's an endothermic reaction. The energy is coming from the environment and going into that reaction to make it happen. Okay. And then an exothermic reaction is when this delta H is negative and energy is released. Okay. So for this molecule, if we're breaking this bond, we have to put in 58 kilocalories. That's endothermic. If we're making this bond, we get out energy. This reaction will heat up. And also notice our units. We get out kilocalories per mole. Okay. So per unit of molecules, we get out a certain number of energy, a certain amount of energy. So I think the most important thing on this slide is that if the delta H is positive, energy is added, that's endothermic. If the delta H is negative, that's exothermic, energy is released. That's the most important thing on this slide. And you will have to know that for these questions and the test. can't remember how far I need to go. Questions so far? This is just kind of like something you know. So this is something that I would put on my note card so that I don't get it flipped on the test. Because that's happens. Okay. All right. Okay, same thing. We're gonna skip some of these things. All right, so let's look at these examples. So the top one, is the top one exothermic or endothermic?
Endothermic?
No, exothermic.
What do we think? So it's negative. If it's negative, what happens?
Oh, the top one.
Yeah, the top one.
Oh, okay.
Very top one. Sorry.
Okay.
This one.
Exo.
Exo. Negative means exo. That's all you have to do. So if it's exothermic, is energy released or absorbed?
Release.
Released. Energy is exiting in an exothermic reaction. Then we feel it. It's coming out. We feel it. And it feels warm. Okay. Next one.
Endothermic.
Endothermic. So it's positive. Endothermic. So would heat be released or absorbed? Absorbed. So this reaction would, if we were feeling it, it would feel cold. Energy would be coming from the environment into the reaction to make it happen. Okay, and then the last two are both negative. So what does that tell us? Oh, I'm using the wrong button. Exo. Good. These two are exo. Energy is released. Exiting. Negative. It's coming out of the reaction, moving to the left. Feel warm. Okay, does that make sense? Okay, that's something that's like kind of you have to memorize it. So that's the fact that endothermic is positive, exothermic is negative. I would put that on my note card. Okay, or I would memorize that. Okay. All right, we're talking about that. Okay, let's go to our examples in Alex. So this one is, we're looking at calculating heat of reaction from molar, this one. Is that the right one? I think it is. Yeah. Calculating the heat of reaction from molar reaction enthalpy and the mass of a reactant. Okay, so let's look at what this looks like. So it says, a chemist measures the energy change, delta H, during the following reaction. So that's something that you can measure. You can measure how much energy is released or absorbed by your reaction. And so we have this chemical reaction, and this is our delta H. So we're going to look at delta H. Delta H is negative, so the first thing we have to do, the reaction is exothermic. Exothermic negative. Exothermic negative. Okay. All right, this box. Suppose 99.4 grams of NO2 react. Will any heat be released or absorbed? So this question is never no. Don't ever put no, okay? So it's yes or yes, but we have to decide, is it absorbed or released? So this is going to tell us that.
Absorbed or released.
Exothermic means release, exiting. So that means we can feel it. Like a fire is exothermic, we feel the fire's heat. It's exiting the reaction. So yes, released. Okay, then this is the tricky part. We have to figure out how much energy is released. So this is, we have to use chapter 5 information to do this problem. So let's go over here. So this one says, if you said heat will be released, you better say yes. Then so you're gonna answer this question. Calculate how much heat will be released or absorbed. Round your answer. So let's go here. So this is where we're gonna look at the units on the numbers. Okay. So this equation tells me, well, let's see. So 99.4 grams of NO2 reacts. So let's write that down. That's what they gave us. 99.4, right? Yeah. 44. I think I said 2 and of NO2 react grams. Okay. This chemical equation is telling me that for 2 moles of NO2, we get out negative 55.3 kilojoules. So this is where we have to go back to moles, okay? This is telling me in moles. The chemical equation is always in moles. We can't measure in moles on our scale. We need to use grams. So the first thing that we need to do is we need to convert this number to moles. Okay. So to do that, does anyone remember how to do that? So we're going to need to get this to moles. Moles of NO2.
This is a simple, easy way of doing it fast. You just take the grams and just divide it by the molar mass.
Yes, that's what we should do. Right, yes. So we're going to take this number. Yes. So for every 1 mole of NO2, we need to figure out the number of grams of NO2. So this is where we say the grams of NO2, we're going to take N plus O plus O. And that's how many grams for 1 mole of NO2. This is our molar mass, okay? So use our molar mass. I don't know, that looks like division. We'll get rid of that. We'll just say molar mass. Okay, so that will give us moles of NO2. Do you remember that from chapter 5? We had to use the molar mass. Okay, so we're going to go to our calculator. We're going to take that number, 99.4. We're going to divide by our molar mass. So our molar mass, remember this is the one where we use our fancy Alex button. We need nitrogen plus oxygen times 2, or oxygen plus oxygen. I'm just going to do it twice. Do you remember that?
Yeah.
Okay, so this is how we're converting from grams to moles. This is our atomic mass is grams per 1 mole of the atom. So hopefully that does the order of operations how I want it. So this is 2.16 moles. Okay, so I'm just going to keep that number. We'll write it. Oh, I have it. We'll write it over here. So that's 2.16 moles of NO2. Okay, and then this equation is another conversion. We have for every 2 moles of NO2, we get out negative 55.3 kilojoules. So I'm going to take this number. This is how many moles we used. This is how many grams, but this is the same number in moles. So it's like feet and miles we just converted. So I'm going to take my number in moles. Okay. And we need to find how many kilojoules. Okay. And then this is from my chemical equation. It says for negative 55.3 kilojoules, we
should have a negative on
2.
it.
Yes, it should have a negative.
Well, on the answer,
I think it should still have a negative. Does it not like it? Let's try it. I'll put it in mine. Okay, so does that make sense? So for 55.3 kilojoules, that's how many kilojoules for 2 moles of NO2. Okay, are we seeing where we're getting these numbers? We're okay? Okay, all right. So let's plug that into our calculator now. So I'm just going to take this number.
Wait, I have a question.
Yes.
Why is there just 1 mole of NO2 on top of that one?
So that is the molar mass. For 1 mole of NO2, it takes a certain number of grams.
But
to
then
get 1 mole.
there's 2 there because that's
Because that's in the chemical equation. Yeah, good question. Okay, so times, I'm just going to not round, times by this number. It should be okay either way. Divided by 2. This is a negative. Does it let me do negatives? Okay, I think it should be negative. I'll put it in as negative in mine and we can see what it is. All right, then this has 3 significant digits. This has 3 significant digits. So this number needs 3 significant digits. It's not going to tell you to round on the test.
Oh, it already has one.
Oh, it already has a negative. Then don't put it twice. Thank you. Oh, did I put it or did it put it?
You put it.
Oh, okay. I don't remember putting it, so. Okay, so I'm going to put it and we'll see what happens. And I just rounded to 3 significant digits. Okay, so I think you need the negative because that's telling you heat is released coming out of the reaction. Okay, questions on that? Okay, let's try another one. Okay, so this one, the chemist measures the enthalpy change, delta H, during the following reaction. So they took ammonia and they split it into nitrogen and hydrogen. And it took 100, or this is the enthalpy, 160 kilojoules. So is that endothermic or exothermic? Okay, that's just a definition. If it's positive, it's endothermic. So that's just like, you have to memorize that or write it down somewhere. And then this one, so say we have 50 grams and 50 grams react. Remember, don't pick no on this one. Is it heat absorbed or released? Absorbed. And that's because it's endothermic. Endothermic is absorbed, exothermic is released. Okay, don't pick no. Unless nothing reacts. I don't think I've never seen that. All right, so then we have to do the math problem, which I keep moving my. Let's do the math over there. Keep moving my erasers. So we have to figure out how many kilojoules. That's what we're trying to do. Okay, there we go. So we're going to start with that number. We have 50.5 grams of ammonia. So the first thing that we need to do is convert that number grams to moles. Use molar mass. Okay, and really we're not just using it, we're dividing. Divide by molar mass. So we need our molar mass for 1 mole of ammonia. How many grams is that? So let's just do the molar mass on our calculator. So nitrogen plus 3 hydrogens. 3 times hydrogen over here. And that gives us 17.02995 grams of ammonia for 1 mole. So we're just doing moles, or grams to moles conversion. So this will give us moles of ammonia. So I'm going to put my number here, 50. The number they gave me, divide by the molar mass that I just calculated. Oops, didn't want to do that. Oh, Alex. Okay. All right, so then this is 2.965 moles of ammonia. Okay, and then we need, the next thing that we need to do.
Do we need 3 on the?
Yes. Yes. This is an intermediate calculation, so I don't want to round too early. So usually what Alex tells you is you want to keep 2 extra. So really, we should keep 5 so that it doesn't mess up our math. Does that make sense?
Yeah.
Oh, you don't want to like round before.
Yeah, you don't want to round. Yes, right. Usually that doesn't affect it, but just because it's an intermediate step. I think Alex recommends keeping 2 beyond what you should. Okay, if you can just keep whatever's in your calculator too, that will work. Until you're done, then you can round. Okay, so this is telling us for every 2 moles of this ammonia, we will get out 106, or we need 160 kilojoules because energy is going in absorbed. So let's take this number now. This is how many moles of ammonia. So let's see, this would be like use mole kilojoule ratio from the chemical equation to find kilojoules. So we're going to use, it'll be like this, moles times kilojoules per moles. Those kilojoules. All right, so that's our moles from our equation, 2.965 moles of ammonia. And our chemical equation says we need 160 kilojoules for how many moles? 2. Again, this one's 2. 2 moles of ammonia. Moles of ammonia cancels out, we'll end up with kilojoules. So if you can follow your units, that would be helpful. So I'm just going to take this number, times by 160, divided by 2. All right, and then we need 3 significant digits. Now I'm going to round to 237 decimal. And it already has kilojoules. And this one will be positive. So sign matters here. It's telling me if the energy is going in or out of the reaction. So let me check. Okay, questions on themes? Yes.
How do you get to 17 point? Is that the molar mass?
That's a molar mass, yeah. This number is nitrogen plus 3 hydrogens. And that's just from the periodic table.
Okay.
Yeah, good. Other questions? Are we seeing where pieces are coming from? Are you okay? Okay. All right. Do you want to do another one of these, or do you want to do the next type? Yes.
I think I figured it out why they love it. So looking at the explanation, it always wants a positive, but if it's exothermic, it still marks the current of this negative.
Oh, okay.
So explanation there will always say it's a positive number, but for exothermic, it sets the negative.
Okay. Okay, maybe because it's talking about release. If you say it's released, then it's negative release, then it's like negative.
That's
Okay.
That's why it works out. So it can be.
Okay, so if you always put positive, then it'll be fine.
Yes.
Okay. So you can always, that's great. Always put a positive and that's always safer. Okay, thank you. All right, let's see. The next one is interpreting a reaction energy diagram. Let's do this one, and then we'll stop today for today. Interpreting. Okay, this one's pretty easy, I think. So this is an energy reaction diagram. So this is our products, or excuse me, this is our reactants. This is where we start on the left. This is our products where we end. So A plus B is where we start, C plus D is where we end. So products, reactants, reactants and products. Okay, so this one, what we have to figure out is where it's starting and where it's ending. So if it's like this, we're going downhill. This is an exothermic reaction. Okay, so I think I have slides on this. Let me just draw some. That's easy enough to show you. So if our products are lower in energy, that's an exothermic reaction. So this is endo. Oh, it's not endo. This is exo. Whoa! This is exo. Okay, and then this one. So the other way, if your products are lower and your reactants are higher, this is endo. So remember, in an exothermic reaction, delta H is negative. In an exothermic, excuse me, that's exothermic. Endothermic reaction, delta H is positive. Okay. So that's our reactants and that's our products. All right. So part of, and again, so that's something that you have to know. That's just like definition. So either put that on your note card or memorize it.
And delta H means changing heat, right?
Delta H is, yes. So let's answer this question. Is the reaction endothermic or exothermic? So if products are lower, this is exothermic. Okay, that's just a definition. You might want to put a picture of the graphs on your note card. All right, heat of reaction is always our products minus our reactions. That's the difference, okay? So wherever our products are, we're going to take that and then subtract our reactants, okay? And so the sign matters here. So here, our products are 200. That looks like the reactants are 250. So products minus our reactants. So 200 minus 250 is what? Negative 50. Okay. And I don't remember how Alex wants our significant digits. Oh, this is subtraction. Okay. So this has no decimals. This has no decimals. So because it's subtraction, we'll have no decimals. We keep the least amount of decimals for subtraction and addition. So I think that's how we'll do it. Okay, activation energy is the difference between the very top of your graph and your reactants. That's your activation energy. So it's like the amount of energy you have to overcome to get to the products. So a reaction always has an activation energy. So activation, and that's always positive. So this one needs to be positive, and it is the top of the graph minus the reactants. So here, next scroll. The top of our graph is at 300. The reactants are at 250. So 300 minus 250 is also 50, but it's positive. You should always put yes on these answers. Just never know. Okay. Can you determine the activation energy of the reverse reaction? So this is just, we're going to flip the reaction. So we're saying, oh, actually now, the products are my reactants. So if we're going backwards, and we'll talk more about this next time with equilibrium. If we're going backwards and we're going from C to D to A to B, then now the top of my graph is still the same. My reactants are now C and D. So top to the reactants would be 100, but it's still positive. So top to my new reactants, my backwards reaction, yes, it's 100. No decimals because nothing has a decimal. Don't put no on these, okay? This is always a yes. Questions? Okay, like I said, better check it, make sure I'm telling you right. Oh, let's see. Oh, I don't need to put a decimal point. I don't know why sometimes it requires that. Okay, so don't put a decimal. It still marked it right though. Okay, questions on this one? Do you want to do another one of these or do you want to do some work time? Work time? Okay. All right, I will wander around and answer questions if you need. We will start on the interpreting. Oh, we did that one. We'll look at drawing reaction energy diagram next time. Oh, okay.